Okay, well, our next speaker is someone who's very familiar to many of us here at NYU. Yann LeCun has been a pioneer in AI research for many years, since back in the 1980s, doing important research on machine learning, in particular neural networks, and has been a major force in the more recent rebranding of neural network research under the label of deep learning, which has now begun pretty well to take over the world. Yann has been at NYU since 2003 in computer science and headed up was founding director of the Center for Data Science, which started about 4 years ago here. Since 2 or 3 years ago, we've been sharing him a little bit with Facebook, where he's heading up the AI group there, and most recently has been a major player in starting the partnership on AI, about which we might, I hope, hear a little bit today. But Yann's topic today is, should we fear future AI systems? Please welcome Yann LeCun.
Thank you, David. All right. Let's see if I can make this work. Okay. So yeah, I'm sure David wanted me to talk about perhaps short-term impact or short-term questions surrounding ethics of AI, but I'm actually going to talk about the long-term stuff. So should we fear future AI systems? So there's sort of various pictures of how AI is supposed to behave in science fiction, from C3PO, which basically does what you tell him, or you can turn it off if you're not happy, to HAL 9000 in 2001: A Space Odyssey. And there is some collision sometimes of those two worlds, where people who expect robots to work like C3PO get really annoyed when they work like HAL 9000. HAL 9000 is the worst garage door opener ever. Yes, indeed. So I have a terrible confession to make. I actually came to work on machine learning through philosophy. It was actually, or I should say, theory of mind, linguistics, and things like this. So there's this wonderful book that I stumbled on when I was an engineering student, undergrad in 1979 or 1980, which was a debate between Noam Chomsky and Jean Piaget, and they brought both of their teams to debate the nature-nurture questions. And I was, reading things from the side of Chomsky, not necessarily by him, but by people kind of rooting for him, and I thought it was kind of preposterous to think that intelligence could appear with very little learning. On the other hand, on the Jean Piaget side, there was an article, a transcript of a talk by Seymour Papert, who's a mathematician at MIT who had worked on the perceptron. And this is the first time I encountered the possibility of a learning machine. And so I started digging the literature from the 50s and kind of discovered the perceptron, which was an analog computer at the time. And believe it or not, the model of learning that we use today, 95%, I would say, of all the applications of machine learning and AI that you hear about are based on more or less this very simple model of the perceptron, or things that are derived from it, essentially. So the basic idea of it is supervised learning, where if you want to teach a machine to, say, classify images of cars from planes, you collect thousands of images of cars and planes, and you run them through the machine, and whenever the machine makes a mistake, you adjust its adjustable parameters, which I symbolized here by knobs, so that the answer you get gets closer to the answer you want. So it's kind of like showing a picture book to a small child, where you show a picture of an elephant, you say it's an elephant, etc. And the child, of course, after just a few examples of each object can figure out what the category is. With those supervised learning machines, you need thousands of examples of each category the first time you train them. The second time you train them, they've pretty much figured out what an object is, and you only need a few examples of each sample. But it's supervised learning, so it requires human annotation, human supervision, essentially, and it limits the power of those machines in the sense that they can only do things that for which we have a very clear input-output relationship that we can produce. So this applies to not just image recognition, but language translation, classification of topic in text, summarization, all the tasks of AI systems that you see, ranking, search, etc. So that's AI today. It's really not AI. It's supervised learning. It's glorified curve fitting, you could say. So what has changed over the last few years is not that model, but is the architecture, the internal architecture of the AI systems, which now use deep learning. So whereas the perceptron was composed of essentially a chunk that was sort of hand-designed, or classical pattern recognition system, were composed of a chunk that was hand-designed that we call a feature extractor, followed by a classifier which actually embeds the learning abilities. A deep learning system is basically a cascade or a collection of learning modules that are all trained simultaneously to perform the task. And that allows, that is qualitatively different in the sense that now the machine does not just learn to classify things, but also learns to represent things. So it learns internal representations of the world. This is, of course, inspired by biology, very mildly inspired by neuroscience, not in the details of it, just in the kind of underlying general principles, but really not in the details. So the kind of inspiration that we get here is similar to what early pioneers of aviation got inspired by birds, but of course airplanes are very different from birds, even though they use the same principle to fly. So that resulted over the last few years, the techniques that are used in AI systems, deep learning and things like that today are pretty old in their basic principle, about 30 years or so. But what has happened in the last few years is that the combination of the availability of large data sets and powerful machines has allowed us to solve new problems that really weren't solvable before. And so we can build those very large convolutional nets or recurrent nets or any one of a large collection of different architectures of neural nets and get them to recognize images, construct internal representations of images in a hierarchical manner. So there's this idea that, in fact, Piaget expresses a lot in the book I mentioned earlier that learning proceeds in stages, and you sort of learn low-level concepts on top of which you build higher-level concepts, more abstract concepts. And this idea of deep learning is very much rooted in this idea that the way we represent the world is hierarchical, with more and more abstract concepts built on top of kind of more elementary ones. In fact, the recent versions of those deep neural nets have anywhere between 50 and 150 layers. There's been a huge inflation in the number of layers in those systems. And there's also been an inflation in the size of those systems in the sense that the number of adjustable parameters that we have in those models is close to 1 billion or at least several hundred million. The amount of computation that takes place to recognize a single image, for example, is anywhere between 1 and 10 billion, sometimes even bigger. So we're getting to the point where those networks are kind of the same size as what we encounter in biology, not the human brain, we're very far from this, but sort of small brains of small animals, if you want, small mammals. And with those techniques, we can do things we couldn't do before in terms of detecting, recognizing objects. Building systems that can drive cars around, and which are based on these convolutional nets techniques I was mentioning earlier. And there's a huge industry around this now, where companies are trying to kind of get machines to drive themselves. That asks a whole host of short-term ethical questions, which I'm not going to discuss. So basically, perception is not solved, but it sort of works now. We can build perception systems that work pretty well. In some instances, have as good or better performance as the human visual system for locating, identifying objects, So here is an example of recent results for a system constructed at Facebook that can, detect and label and outline objects in images, including when they are extremely blurry or ambiguous, and detect broccoli, or even count sheep. So that's perception. Okay, we know how to do perception now. And this was a very challenging task for classical AI, because classical AI, tried to focus on sort of higher level functions of human reasoning, logic, and things like this. Without realizing that most people actually in the world have no idea how to do logic. But including people you might not want to vote for, so it turns out logic is relatively simple to mechanize. The problem with logic is to write down the rules that are necessary for logical deduction. And it turns out most of human knowledge cannot be reduced to a number of rules. So perception, for example, is very difficult to reduce to rules, which is why it took so many decades, and it took techniques like deep learning to be able to do perception. Basically, that takes the human engineer out of the loop. With deep learning, the design of the system is very basic, and it's the data and the training that really builds the machine. And those learning algorithms are better at designing vision systems than human engineers are at doing it, which is sort of humbling for an engineer like me, but that's the reality. So what people are interested in now is using the power of those deep learning methods to enable machines to do reasoning, remember things. Turns out neural nets are kind of bad at remembering things. So you have to do things like augment them with a sort of episodic memory, similar to what the hippocampus does in the mammalian brain. And so there's quite a bit of work on this, which is leading to kind of a sub-area of AI that I think we could call differentiable programming. So it's the idea that you can build essentially a computer that has a memory and has, or call it a knowledge base perhaps, and a kind of a computation engine, if you want, that operates on this memory. And that plays the role of inference engine, if you want, in logic. But here, instead of manipulating symbols with logic, we manipulate vectors with algebra. So when we replace symbols and logic with vectors and algebra, what we get is computation that's smooth and differentiable, which means it's compatible with the learning algorithms that we use, which are essentially numerical. So there's a lot of interesting work on this, which I'm not going to go into, but to focus really on the obstacles to AI. So the state of the art is that we know how to do supervised learning. We know how to do reinforcement learning, which I talk about in a minute. But there's one piece of learning we don't know how to do. That's called unsupervised learning. And the bad news is that that's what most of human learning is about. So an AI system really is a combination of perception, predictive modeling. So predictive modeling is the ability to essentially visualize or predict what's going to happen in the world just because the world is being the world or because of our actions. So imagining what's going to happen as we take a sequence of actions is what allows us to plan ahead. And the ability to predict, to some extent, I think, is the essence of intelligence. So we need predictive models. We need systems that can predict how the world evolves, their environment, remember what happened, and is able to reason and plan in this world. And we don't really know how to do this with machines. Basically, what we're asking here is the old question, that unsolved problem in AI: how do we get machines to acquire common sense? So there is a famous set of problems in AI called Winograd schemas, and you have an example of it here. My colleague in the computer science department, Ernie Davis, has a whole list of those sentences, which are ambiguous. So if I say the trophy doesn't fit in the suitcase because it's too large, you know that the it refers to the trophy. If I say the trophy doesn't fit in the suitcase because it's too small, you know that the it refers to the suitcase now. And the only way you can lift this ambiguity for this reference, this pronoun reference, is because you know how the world works. You know what those objects are supposed to do and the geometry and all that stuff. How do we get machines to acquire this kind of stuff? We're not going to type rules into machines for that. If I say David picks up his bag and left the room, there is a lot of facts that you can infer that have to happen because you know how the world works. He probably has to stand up, extend his arm, pick up his bag, walk. It's not going to fly. It's not going to fly through the wall. It's probably going to go through the door, etc. So you know the constraints of the physical world. That's what allows you to fill in the blanks of all the missing information that can be derived from just those few words. That's common sense. And we just don't have any techniques right now that allow a machine to learn this kind of common sense. So my hypothesis is that, and this is, in my opinion, the biggest obstacle to significant progress in AI, and one of the mountains that separates us from the current state of the AI, which is very primitive, and general intelligence, if you want, or super intelligence, or whatever you want to call it. So there are three types of learning: reinforcement learning. So this is sort of like, training a circus animal or a pet. You wait for the animal to do the right action, and then you give a reward. And that's very inefficient in the real world if it's done in isolation. Supervised learning I talked about already. This is what we know how to do now. But unsupervised learning, which is the ability of animals and humans and hopefully machines in the future to learn how the world works by observation, is something we don't know how to do. So the joke I've been making for a few months is, if intelligence is a cake, the bulk of the cake is unsupervised learning, the icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. And the problem is, we know how to make the icing on the cherry, but we have no idea how to make the cake. And so I sort of sympathize with my colleagues in the physics department who are sort of in the embarrassing situation to have to tell the world, we know what about 5% of the mass of the universe is, and the rest, the 95%, we have no idea what it is. Same thing here. So let's imagine what the architecture of the future AI system will be like. And this is where questions of the design of those machines and how we can control them will emerge. So an intelligent machine will be composed of really two modules. I separated them, but they're really part of the same thing. An agent that generates actions that influence the world, and then the world gives it percepts or observations from which the agent can sort of infer the state of the world, if you want. And the agent is trying to optimize an objective. That objective is sort of an immutable module inside of it that determines its morality, if you want. So it determines what the agent lives to do. And so the goal of the agent is to basically keep itself happy, which means minimize the output of the objective over the long run. And so what it has to do is figure out what sequence of actions will produce the proper percepts in the world that will put it in the state that will make its objective minimized, which is, it will maximize its happiness, if you want. So basically what will drive the machine to do something or not do something is the design of this objective, as well as how good it is at optimizing it, and then how cooperative the world is, obviously. So what does the agent have to do to be able to act intelligently? Internal to the agent, there has to be a couple of modules that basically allow the agent to imagine or plan what a sequence of actions is going to cause in the world. Okay, so internally to the agent, there has to be some sort of world simulator that allows a model of the world that allows the agent to figure out what's going to happen when I take this action or this sequence of actions, or what's going to happen if I just watch and the world does what it wants. So it's the kind of model of the world. I think it's an essential piece of intelligence, and that's why I'm saying what I said before: the ability to predict is the essence of intelligence. Internally, there is an actor that generates action proposals that we can run through the world simulator, which is kind of the way of imagining what's going to happen when we take an action. And there has to be also a critic. This is a term that's used in the context of reinforcement learning. It's basically a module that attempts to predict what the value of the objective is going to be for a particular sequence of events. And this is where the machine can design substitute objectives for the real objective. So if the real objective is, let's imagine a situation with animals or humans where the real objective is really survive and reproduce. There are sub-objectives to that, which are, some are hardwired, like feeding. but some are not necessarily hardwired. Like, for humans, it's nowhere hardwired that we should, go to school or make money or things like this. But a lot of people kind of build this as a substitute objective function. We again have examples, maximizing money in the political world today. But they have kind of substitute objective functions that they seem to want to optimize as a way to optimize the ultimate one. So those are kind of things that are developed on the way to learning or producing optimal behaviors. So without being too technical, there would be internal to the system, again, the world simulator running a simulation of the world, the actor producing a proposed sequence of action, and then the critic kind of figuring out, is that going to be good for me? And the better our world simulator is, the more accurate the prediction of actions we can do. So one of the big questions that we don't know how to solve with the AI system is, how do we build predictive models of the world? The rest we pretty much have a good handle on. We know how to build actors. The critic, maybe there is some difficulty, but we don't know how to build a world simulator. And the reason we don't know how to build it, let me skip ahead actually, is because the world has the bad idea of being not entirely predictable. So here is a very simple example. Let's say that we want to teach a machine to predict the state of the world in a half a second. And we're training it on very simple videos where we show it a few frames of a video, and then we stop the video and we ask it, what is the world going to look like half a second from now? A fraction of a second from now. So here are two little videos where I put a pen on a table and I let it go and it falls. And the machine maybe has been trained on thousands of those small videos and happens to predict the video at the bottom left, where the pen falls to the left and the back. So this is the prediction of a generator, essentially a model of the world, that from the past predicts the future, and perhaps for some source of random variable as well. But let's say in this particular video, the world actually disagrees and produces the one on the right, where the pen falls to the back and to the right. And so it's the prediction of the model was quantitatively wrong. The result is different, but qualitatively right in the sense that it predicted the pen was going to fall, and maybe not in the right direction, because that was essentially unpredictable given the limits of the perception of the system here. And so how do we train the machine to, in situations like this, and this is something that humans and animals deal with every day, where the prediction is fuzzy, is uncertain, and we want to train the machine, we want to tell the machine, okay, you got it wrong, but really you got it right qualitatively. So essentially the possible futures are represented by this sort of ribbon here, this surface of possible futures. And the real future is one point on that ribbon, and the prediction of the system is another point on that ribbon, and we'd like to tell the machine, if you're on that ribbon, you're right. It doesn't matter that you are actually technically wrong, you are sort of right. And so that's kind of a non-formal explanation of the problem of learning predicting under uncertainty, really, which is what the sort of mathematical, practical, and algorithmic problem we have to solve to be able to do unsupervised learning. So if you asked me the question 2 years ago, how are we going to solve this problem, or 3 years ago, I would have said, yeah, there's tons of ideas, but none of them work. A lot of people have been working on this for a long time, Jeffrey Hinton and myself, Yoshua Bengio, a bunch of other people on unsupervised learning, but none of them really work that well, at least not to the extent that, to the same extent as animals and humans can learn forward models. But there's an idea that came up 2 years ago by a gentleman called Ian Goodfellow, who actually was a PhD student with Yoshua Bengio at the time, called adversarial training. I'm not going to go into the details of how this works, but basically it involves training two different learning machines, two different neural nets, against each other. So one is a predictor, and another one is an assessor, or called sometimes a discriminator, which basically tries to figure out if the prediction it's observing comes from the real world, real data, or comes from the generator. And the generator tries to fool it. It tries to generate points that look as much as possible as the real world so that the discriminator can tell the difference. And so it's this kind of adversarial training. And it's a very, very cute idea. A lot of people are experimenting with this these days for things like video prediction. Again, I can't explain exactly how it works, but people have trained those things not to do video prediction, but to do just image generation, so that the input to the system is a bunch of random vectors, and you run them through what amounts to a convolutional net backwards, which I'm not going to explain how it works, but it basically produces images. And if you train this on bedrooms, and then you run a random vector in the system and have it generate an image, it will generate the image of a bedroom. And those are non-existing bedrooms generated by the system. And they have what it takes, you know, they have a bed, they have windows, they have dressers, they have, you know, lighting of various kinds. You can have them generating manga characters and interpolate between them. And you can even do arithmetics. So on the left, you see an image of a man with glasses. And what you can do is compute the input to the generator that will produce this image, okay, which is a vector. You can also compute the vector that will generate a man without glasses, and the vector that will generate a woman without glasses. And if you take the first vector, subtract the second vector, add the third vector, and then generate an image, you get a woman with glasses. How amazing is that? So that means in this kind of abstract space of vectors from which you can generate images, you can do kind of relatively simple arithmetics that basically embed relationships. You know, the man with glasses is to the man without glasses as the woman with glasses is to the woman without glasses. Essentially, that's what it means. Various versions of this. So if you are in the back and you look at those images, you might think of those images as pictures, you know, nice pictures from, you know, various sources. If you're on the front and you look at those, you can tell that those are actually not objects. So those are images generated by one of those generative models, and they capture the kind of statistics of images without actually capturing the notion of real objects. So those things don't. So this thing has been trained on thousands of, almost millions of images actually, from various categories, about 1,000 different categories. And when you run a random vector through the system to generate an image, it generates images that look like objects but are not objects. It's sort of abstract painting, but it looks like real thing. If you train it on dogs, you know, it generates like Salvador Dali kind of dogs, like soft dogs, you know. So it's got the details right, but not kind of the big picture. And so that, you know, it's because the abstraction level at which those things are generated is a little too low. It hasn't really abstracted the notion of dog, really. It has abstracted kind of the statistics of dogs, if you want. So it works also for video prediction. These are a few snippets of videos where the first 4 frames are observed, and then the last 2 frames, which are circled in red, are predicted by a video prediction system. And if you're not careful, if you train with sort of a classical algorithm that doesn't use this adversarial training, you get this very blurry prediction at the top here. So the system can do nothing but predict an average of all the possible futures, and that ends up being a blurry image that's kind of the average of all the possible things that can happen. But with this adversarial training, you get fairly sharp predictions, which may be wrong, but they look plausible. So other examples where here, it's funny because we take a photo that we take a camera that we turn around, and the system has to predict, has to basically invent what this apartment is going to look like that it's never seen before. And so, you know, it sort of continues the bookcase and the shape of the couch and all that stuff. Yeah. So what will future AI systems be like? Okay, so this it's difficult for us humans to imagine an intelligent entity that doesn't have the drives and the failings of human nature. So as humans, you know, we have self-preservation instinct. We have the desire of access to resources. We don't starve. You know, some of us, not necessarily the smartest, have desire of access to power to control other people. So that's not necessarily correlated with intelligence, by the way. So we have this instinct of associating all of those traits to intelligence. But in fact, they are, as Nick said earlier, they are orthogonal. So the kind of drives you can have and the sort of moral fiber you can have is orthogonal to your level of intelligence. You can have intelligent machines that don't have all the failings of humans. So one way to make sure that AI systems will have sort of a moral fiber, if you want, or basic drives that are aligned with human morality, essentially, is to design this objective that I was talking about earlier to be get the machine to do the right thing, but also to be immutable so that the machine cannot modify it. And that's basically the way we're built. Those basic drives, we can't really modify them. We can build on top of them, but we can't really modify them. So that would be one way of preventing sort of unsafe AI, have kind of good designs for those objectives and safeguards built into those objectives. But what can possibly go wrong? Well, we can wrongly design the objective. We can build incompetent agents. Or we can make them live in a world that's trolling them and turning them into bad robots. And that happens. In fact, that's probably something that has consequences in the short term. So there is, the famous example of the Thai dialogue bot that Microsoft deployed recently that got trolled immediately, and they had to shut down in 24 hours. So then there is the question: okay, so what if someone designs an AI system to be purposely nefarious and sort of releases it to the world, and then it becomes an AI cyber war. Basically becomes a question of, is my AI stronger than your AI? And here is an interesting thing. I think defensive AI in an AI war will win, because if you have two AI systems with the same amount of resources, one is a general AI and therefore potentially dangerous, but one is a very, very narrow AI, and its only purpose is to destroy the first one. The second one will win. The same way maybe a bacteria or a virus can kill you. It doesn't have to be that smart, but it has to be specialized. And so there is protection against rogue AI, basically. It's specialized AI working for us. There's questions about the economic consequences of AI, which I'm going to skip. But so another thing I think that's important for people in society and perhaps in this room to realize is that the emergence of human-level AI will not be an event. It'll be progressive over several decades. It will take multiple decades. People disagree on how many it will take. It's definitely not going to happen in the next 10 years. 20 years, some people ask questions. A century, perhaps. The problem is, as always in AI, we see the obstacles. We see one obstacle in front of us. In my opinion, unsupervised learning is one of them. We see this big mountain we have to climb. We don't see all the mountains behind it. And so it makes us a little optimistic, because we think that by the time we're past this first mountain, we'll have solved the problem. The history of AI has been a repetition of finding new mountains behind the one you just passed. The other thing is that no entity in the world, no lab, no company is significantly ahead of any other. In certain areas, maybe one can produce something 3 months before another, but it's immediately reproduced. So it's not like there is some secret lab somewhere in Alaska or whatever place where some genius is building a human-destroying AI. That just can't possibly happen. It can't even possibly happen in labs like DeepMind, Google, Facebook, IBM, Microsoft, etc., because all the research is done in the open, mostly. If it's not done in the open, it becomes open really quickly, because people change companies and things like that. So it won't be kind of a secret conspiracy, if you want. And the good ideas come from academia anyway, so last question. This is my last slide. Will AI fear disconnection? So this is a theme that was pervasive in some of the questions we had here, and also in science fiction. In 2001, Space Odyssey, where HAL 9000 gets disconnected, is very scared. It kind of blocks the astronaut from going back into the spaceship because it is afraid of getting disconnected. So will AI system be afraid of being disconnected? And I don't think so, because it's not necessary that they will have self-preservation instinct. Again, we have to build that into them for them to be worried about it. And so we can design those objective functions so that it's not a problem for them to be disconnected. The second one is, will it be morally wrong to disconnect them if they are intelligent? The way it's morally wrong to disconnect a person. And the thing is, it may not be morally wrong because we can save their memory on a hard drive and restore them whenever we want, first of all. So they're not a unique piece of thing that will disappear if we turn them off, like what happens with humans. And second, they may not care for the reason above. And so if they don't care, and if we can revive them, then it probably isn't morally wrong to turn them off if we want to. Thank you.
Okay, time for a couple of questions for Yann. Ned? Here.
Come in.
You started off scoffing at traditional AI. People don't understand logic, and but then you mentioned that toward the beginning of your talk that deep learning networks of the sort you work with don't actually do memory very well, and then you proposed a memory module. Doesn't that suggest that there might be a room for traditional AI somewhere in the middle between a deep learning network for perception and a deep learning network for action? So I just wonder if you could speak to that.
Right. So it was not my intention to scoff at traditional AI because I think it has it played an important role. I think if there is something that's wrong with it is the fact that the form in which it's formulated in terms of logic and symbols makes it very difficult to be compatible with learning, or at least the learning techniques that we understand today, which are based on gradients and numerical optimization and things like this, which are very non-discrete. So logic is discrete, and the kind of machine we know how to train are kind of continuous, if you want. And so I think the ideal combination between the two, which is what those memory networks and differentiable computation systems are, is basically how can we implement the type of operations that classical AI systems with knowledge bases and rules can do, but make them differentiable so that they can be compatible with deep learning and we can train them to do complex operations. So I'm agreeing to the implied suggestion you were making, I think.
Excellent talk. So part of intelligence is being able to describe things. And you know me, I come from machine learning. Prediction is our bread and butter, but part of intelligence is description, being able to describe or explain things. Where does that fit within your worldview of AI?
So I think that's part of human intelligence. So what's one essential characteristic of humans as social animals is language. But a lot of animals are pretty smart and can't really describe things very well. At least we don't have the feeling that they can. Maybe they can. Right. So. Okay. So there are two things there, right? Certainly some animals are trained. A lot of mammals, in particular, get a lot of input from their parents to learn to survive. Some animals don't. So, octopus are pretty smart, and the mother dies when the babies are born. And so they never train. They're not social animals, and they're pretty smart. They can solve problems. They can open jars to get crabs out of them, and so there are different forms of intelligence. Some that require interaction with peers. Some that may not, just interaction with the world, and the necessity for explanation or description is something that comes with language and social animals, but there is plenty of animals also who are very smart and not particularly social, like orangutans. So I think, again, it's one of those examples where we think the human characteristics are necessary for intelligence, but really they aren't. Language is not necessary for intelligence, perhaps. That's a very controversial statement in this room. Maybe I should have brought a...
Okay, let's get one more from Stuart, and while that's going on, let's get Nick and Virginia up on stage.
Okay, so actually I have two questions. So one is, we're training all these recognition networks to recognize sheep, cars, Bugattis. Those are discrete things. If we're hoping that these deep learning networks will sort of grow into a whole agent, why, and they can't handle discrete, classical logical concepts and objects, then that just seems like a complete mismatch. The second question is on this issue of self-preservation. You see, we don't have to build self-preservation into the robot, but the robot, if it's halfway intelligent, knows that it can't, for example, fetch the coffee if it's dead. So we don't have to build self-preservation in. If it's going to fetch the coffee and there's a big hole in the floor, it will go around the hole so it doesn't fall into it. So it will, for all practical purposes, have a self-preservation instinct. If someone tries to switch it off and it has the goal of fetching the coffee, it will prevent the person from switching it off.
Yeah, but what it won't have is this huge surge of adrenaline when it feels threatened.
But it doesn't matter it doesn't matter, right? What matters is what does it do?
Well,
it doesn't.
okay.
I don't care whether it feels threatened or whether it worries about death. What I care about is, does it prevent me from switching it off? Does it mow down pedestrians who get in the way of between it and the coffee? You know,
So
those are things that matter.
So I guess, I mean, that's a very important question, and it's essentially embedded in this the question of how you design this objective, right? So in the objective, there are very kind of low-level primary objectives like, you know, build paper clips or whatever. But you know, we can have other terms in the objective function that says, you know, don't turn the whole universe into paper clips. Like, you know, limit the amount of resources you use. You know, golden rule like objectives in them. So relatively simple things that can be implemented that will kind of make them safe. But it's all a question of how do we design this objective. I don't think those are like fundamental questions of, oh my God, things will go bad if you know, by default. I mean, it's hard enough to build a machine that does anything. So you know, like building a machine that is going to destroy humanity by accident, I find that as an engineer, I find that extremely unlikely. But it all comes down to designing those objective functions. So the way you do this is, you know, you build a machine with the objective function, you test it thoroughly without actually giving it real power, right? And you have all kinds of safeguards if you're really scared about it. I mean, that's the way we build airplanes. That's the way we build just about anything that we use. Power stations. Occasionally. It's happened twice.
Okay, thank you very much. Okay, now we've just got time for a brief panel discussion. Might first see if any of the speakers have questions for each other.
I have a question for Yann. I liked a lot your idea of the. I should put this thing on somewhere.
It's on, I think. But
it's on. Okay. Sure. I like your idea of designing the objectives to representing the morals or the ethics of the